Hello. I hope so that now you can see and hear me. Just 1 second, I try to mute my live lecture. Okay. So good day, and I am really happy that today I can talk a little bit about electricity and magnetism today. I was asked by Professor Marek to substitute him. So today I'm going to be the lecturer. My name is Egerhard László, and I would appreciate it if you could give me some feedback that you can see and hear me. As far as I see, there are 6 people here, now already 5. Are you there? Anyway, I will start. I hope so that it's not only me who is here. And I'm going to share my presentation. It's electrostatic and magnetism. So today, after the introduction, we are going to have 2 main parts, electrostatics and magnetism. Although they are usually taught separately in the elementary and high schools, there are a lot of connections between these 2 topics. However, also here we keep this division. So first, I will purely talk about electricity, and then I will talk about the basics of magnetism. And after that, at the very end of the lecture, I'm going to talk a few words about the connection of these 2 main chapters in physics. So, what should we know about electrostatics? Here we have to start with the concept of electric charge, and it goes back in time to the ancient Greek people. They also already have had some concept about electricity, so they also realized that if they rub some resin-like materials, then it might attract small pieces of, for example, feathers. However, for a long time, people had no possibility to examine electricity in details. The main reason was that they had no consistent source of electricity. Obviously, rubbing electricity, so if you rub something, was present. However, it's not appropriate to produce a large amount of charges. Later on, a few hundred years before, people realized that lightning also represents a kind of realization of electricity. So thereby, they used it to examine, to understand the phenomenon of electricity. And even later, they could prepare the first prototypes of batteries. And maybe this was the beginning of the real electricity. However, even the ancient people could understand a few properties of the electric charge, and today I'm going to start with these basic properties of electricity. And how can we first of all define the electric charge? It's a hard task. It's a physical quantity that is associated with matter. Similarly, just like mass. We know that it's not a real definition because thereby we just categorize the electric charge and we get no actual understanding about it. But first of all, we need to accept this very important feature. The main reason is that electric charge has the same feature like mass in the sense that it's conserved. So thereby it's a very important quantity in physics. And let's see how it behaves. Relatively long ago, it was observed that we can experience two different types of interaction. Namely, charged objects may attract each other or repel each other. If you just think of the fact how it might be possible, then very quickly we realize that we need to have two different electric states which might produce two different types of interactions, and they were called later as positive and negative state. Then in the beginning of the 20th century, it turned out that these two different states are associated with not two different parts of the fundamental pieces of matter, although in the material we have positively charged protons and negatively charged electrons, because out of these two fundamental particles, only electrons are mobile. So it turned out that meanwhile, the negative charge actually means that we have a lot of electrons. Positive charge, the positive charged objects have excess protons, but not because a lot of protons gather there, but the electrons moved away. So we have less electrons, and that's the reason why we have no protons. But this is rather atomic physics. And since it turned out that the electron is mainly associated with the electric charge, then it turned out that the electric charge is at the same time quantized. What does it mean? That there is a minimum charge. And this minimum charge is the charge of the electrons. And each and every charge values is built up so that it's a kind of multiple of this minimum charge of the elementary charge. This elementary charge is a very small value, 1.6 times 10 to the minus 19th Coulomb. Coulomb is the unit of the electric charge. So thereby macroscopically, we do not feel this quantization. We do not feel that the charge changes stepwise. As far as I have already mentioned, charged objects may attract or repel each other, but how can we quantify this? This is explained by the Coulomb's law. Coulomb's law states that the larger the point charges are, the larger this force that acts between the charge of objects. This is called the Coulomb force. And the further they are from each other, so the further they are separated, I mean the charge objects, the less the charge. And this is not a linear dependence, but a quadratic one. So if you move the charge objects twice at a distance of twice as large from each other, then the force decreases by a factor of 4. And what happens if we have not simply 2 charges, but many charges? In this case, we have to calculate the Coulomb force between each and every pair of forces, of charges. So if now we have one central charge. This is denoted by Q, and electrostatic forces, Coulomb forces, are acting on it by many other charges. These are the red charges. Then we have to calculate the Coulomb force according to the previous formula for each and every red charge, and then we have to sum these force components up. This is the superposition principle. And now in the following, we are going to introduce a new concept. This is the field concept. The first question is, why do we need this? Here you see that if we have many charges, and usually this is the case, then we have to calculate a lot, because for each pair of charges, we have to calculate the Coulomb force. Now let's imagine that we replace this central blue charge, and we are going to have a yellow charge with twice as much charge. Then normally we should repeat this process. However, we might wonder that what has actually changed? Only one charge. All the other, the total surrounding remain the same. And this is the basic idea that we should somehow define or introduce a new physical concept that characterizes not the pair interactions themselves, but instead of the surrounding of the charge. And this will be the electric field. So that's why we would like to introduce this electric field. And this electric field is based on the previous superposition principle. So we are going to calculate the total force from the interacting pairs of charges. And then we consider this central force as a probe charge. Probe charge means that we use it in order to map the surrounding, and thereby we can introduce the electric field. The electric field will be equal to this force that we introduce here, divided by the probe charge. So that's the reason why it will not depend anymore on the central probe charge. That's why we call it probe charge. And now the question is, how large is the force acting on any arbitrary charge that we position in the place of this probe charge? Here, this is the formula that will give the answer to this question. It will be the electric field that we determined previously multiplied by this new single charge. So thereby we can separate these pair interactions into a chosen charge and the surrounding. The unit, the SI unit of the electric field, comes from this formula. It's the unit of force divided by the unit of charge. So that's why we use the unit of Newton over Coulomb. And there is an alternative unit. Later you will see what voltage means, but the electric field can also be introduced so that it's the voltage over unit length. So that's the reason why we can measure the electric field also in units of volt over meter. How can we represent the electric field? For this, we have a model. This model is the model of field lines. The field lines is or allow for a graphical representation of the electrostatic field acting in a given region of the space. And we introduce these electric field lines so that the direction of the tangent to these field lines represent the direction of the electrostatic force. And the intensity of the field lines, or the density of the field lines, how close they are running, it represents the field strength. So for example, here, the field lines are close to each other, so that's the reason why why the electric field is large here, and here they are further from each other, so here the electric field line is less. In the following, we are going to use this electric field line concept for describing the electrostatic field acting around point charges, around like and unlike point charges. Here, first of all, we are going to talk about static charges, so they are at rest. And if we just map the electrostatic force around the charges, both the direction and the magnitude of the force is important, then we can determine these types of field lines. As you see, the electric field lines never cross. Why is it so? Because if we imagine such an impossible situation that we have two crossing field lines, then at the crossing point, we should have two options to determine the electrostatic force, because the direction of the force is determined by the direction of the field lines. So it means that here the electrostatic field or the electrostatic force is not clear, not clearly defined. So that's the reason why it's not possible that we have crossing field lines. If we have two electrostatic fields, then they can be added the similar way vectorially as the electrostatic forces. Maybe I have not mentioned that the electric field is also a vectorial quantity, so it has not only a magnitude but also direction. It's simply to understand because it's the force, a vectorial quantity, divided by here constant, by the charge of the probe charge. So that's why it needs to remain a constant, I mean the electrostatic field. And if you calculate the interaction or determine the interaction of the electrostatic fields of point charges, which has such a radial arrangement, then finally we will get this arrangement of field lines around pairs of charges, pairs of unlike charges. Here we have a positive charge, here we have a negative charge. As you see, the further we go from the pairs of charges, the less the electric field. And here in the center, the direction of the field strength is perpendicular to the line separating the two charges. What happens if we have like charges, like two positive charges? We have to follow the same concept. That's how we can determine the net electrostatic field, again from vectorial additions. And maybe I haven't mentioned that conventionally the electric field lines always start from positive charges and always end up at negative charges. What kind of effect does an electrostatic field have? The positive charges that create a positive electric field can attract negative charges. If we approach a positively charged object to a conductor, to a metal, then since this metal contains a lot of free charge carriers, electrons, then these electrons quickly move into an orientation that the field lines are going to be perpendicular to the surface of the metallic object. This is called influence effect, and it raises a quick current, and once the charge carriers move into this position into the second position, then it ceases and it's to a steady state where there is an electric field between the positively charged object and the negative charge carriers in the metal object. What happens if we have a dielectric object? Dielectrics are such objects that do not carry current easily. They can be polarized. It means that although the charge carriers cannot move as freely as in metals, they can move a little bit away within the object. So that's the reason why we have a polarized object, and it creates an internal polarization that is parallel to the external to the direction of the external electrostatic field. And in conductors, this polarization creates a relatively large organization of the polarizable atoms. So this is the meaning of the macroscopic polarization in dielectric materials. And now in the following, we are going to talk about the capacitors. Capacitors were the so-called first batteries. So these were the first devices that were capable to store charges, not for a long time. So it was only temporary storage. However, large capacity capacitors were appropriate to carry out extended measurements with electric current. So this was that point where the first systematic investigations started with electricity. The capacitors, this is a parallel plate capacitor illustrated here. The capacitors consist of two metallic plates separated by some non-conducting material. It can be air or any kind of non-conducting insulator. And it can be shown that the electric voltage defined later, created here, is proportional to the charges that are collected on each capacitor plates. And there is a factor of proportionality between these physical quantities, the charge and the voltage, and this is called capacitance. The capacitance will be a measure, the measure of a capacitor. And in case of a parallel plate capacitor that has such a structure that illustrated in this figure, it can be shown that this capacitance depends on material constants and geometrical parameters. The larger the cross-sectional area of the capacitor plates are, the larger the capacitance of the capacitor, and the smaller the separation between the plates is, the larger the capacitance. And here you see there is another factor denoted by epsilon, or epsilon 0. Epsilon denotes the permittivity of the material that fills out the place or the space between the two plates. And we use the denotion of epsilon 0 if we have nothing between the two plates. This is the permittivity of the free space. It refers to vacuum. However, if we use another material, then we have to insert here the permittivity of the given material. And the capacitors not only store charges, but with this feature, they can also store energy. So that's why I said that they are the prototypes of batteries. And here you see how large is the energy density stored in a capacitor. It can be calculated according to two alternative formulas. Either it's half times q squared over c, or half times c times u squared, where c is the capacitance of the capacitor, q is the charge on the plates, and u is the voltage between the two plates. Here you see what I mentioned, what happens if we replace the vacuum, the free space between the two plates with the material. Then a polarization occurs in this material due to the external electric field. And that's the reason why we need to put here, instead of epsilon 0, the permittivity of the given dielectric material. And it can be calculated as a product from the permittivity of the free space, epsilon 0, and the relative permittivity, which is characteristic to the given material. It's a material constant. Now the next question is, what happens if we have not one single capacitor, but many capacitors? How can we connect it? In electricity, electronics, we have two main ways how we can connect components, electric components. First of all, we can connect them in series. This is the upper part. This is illustrated on the upper part of the figure. It means that we form a kind of chain from these components. And the other possibility is connecting them in parallel. The parallel connection is a kind of combination of the components, so that we connect the ends of the components, and that's how we form a new combined component of the individual elements. How can we obtain the so-called net capacitance for both a connection in series and in parallel? In case of parallel connection, we just have to add the individual capacitances. It's easy to understand because this connection acts as a joining of the plates, so thereby the areas will be added, and the capacitance is directly proportional to the area, the surface area of the capacitor plates. In case of a connection in series, we get the reciprocal of the net capacitance from the sum of the reciprocals of the individual capacitances. So it's a little bit more complicated. Here, this reciprocal law applies to the net capacitance. Just a remark, later we are going to talk about the resistors. For the resistors, it's just the opposite. If we have resistances connected in series, then we just have to sum up the resistances in order to get the net resistance. And if we have resistors connected in parallel, then we have to use this reciprocal law. And now we are going to introduce the voltage. So this is the point where we we go from the electrostatics to the study of moving charges. And here I would like to remind you the flow of fluids. You have already discussed the fluid flow in the physics lecture. And similarly, as we need a pressure difference in order to have a flow of fluids, here we also need to have some difference that represents a driving force for the flow of charges. And this driving force is the voltage. The voltage is denoted by U in Europe, and the unit of voltage is volt, whose symbol is V. Here's the reminder that the current, in case of fluids, or current intensity, was defined as the number of particles or volume of particles or mass of particles per unit time. Similarly, we introduce for fluids the current density, which was the number of particles or mass of fluid or volume of fluid over unit time and unit surface area. Here we are going to do the same. However, here we are going to talk about number of charges. So it's not fluid, number of fluid particles. And this is how we define the electric current. So the electric current is a ratio from the shifted electrical charges to the time. Its unit is coulomb per second, which is called ampere. Similarly, we can introduce the current density, the electric current density, which is the electric current or current intensity over area. So it's the number of shifted electric charges divided by the time and the area. It's also worth mentioning that although the electric current has a direction, the electric current is not a vectorial quantity, but a scalar quantity. However, current density is very often represented as a vector. The electric current is one of the 7 basic units in the SI system. So that's the reason why it was defined. So very precisely it was measured, and then it was standardized. And it was defined so that the current is 1 ampere if it flows in 2 parallel, straight and infinitely long conductors with negligible cross-section at a distance of 1 meter. And in this case, we measure a force between these 2 conductors of 2 times 10 to the minus 7 newtons for each length of 1 meter. And now I have already talked about the cause and the result. The cause is the voltage, and voltage, the reason is the voltage, and the reason and the voltage causes the electric current. And if we determine how the electric current depends on the voltage, then we can realize that there is a proportionality between them. And this proportionality will introduce us the resistance, the ohmic resistance. The resistance is the ratio between the voltage and the created current. Why do we have this resistance? The resistance is a consequence of the fact that the atomic the atoms hinder the motion of the electrons, so they can actually move not absolutely freely within the materials. If this blockage is not so heavy, just like in metals, then the resistance is small. However, in insulators, the free motion is blocked very heavily, so that's the reason why insulators have a large ohmic resistance. Now we can determine what influences the ohmic resistance of materials. If we have a piece of metals, then it's easy to realize that the resistance is directly proportional to the length of the conductor, and it's inversely proportional to the cross-sectional area. If we have a proportionality, then we easily realize that there is a factor of proportionality between the factors. And in this case, this factor of proportionality is the specific electrical resistance, which is measured in ohm meter, which is independent of the geometry. However, it depends on the material. It's a material constant. It gives us how large is the resistance of the wire of unit cross-sectional area, and unit length. So 1 meter cross length and 1 square meter cross-sectional area. And if we combine electrical components in order to form an electrical circuit, then we can state higher level connections between the currents that flow through the individual components and the voltages that can be measured between the connection of each components. And these are the so-called Kirchhoff rules. Kirchhoff's rules incorporate 2 main rules. One is the knot rule or junction rule, and the other is the mesh rule or loop rule. The first one talks about the conservation of electric charge. So the charge retention is the physical principle behind this law. Namely, if we have a junction into which currents flow in and which is left by currents, then the sum of the currents flowing into the junction and the currents leaving the junction should be 0. This is a kind of signed sum, so that the incoming currents have a sign of have a positive sign, and the currents leaving the junction have a negative sign. Or if we work with the absolute values, and we can also say that the currents coming into the junction are equal in magnitude to the currents, the sum of the currents leaving the junction. Here you see the loop rule, which states that the sum of the voltages, these can be both voltage rises and voltage drops. We have a voltage rise between the 2 connections of, for example, battery. We have voltage drops between the 2 connections of a lamp or any kind of resistance. So the sum of the voltages around the closed loop is 0. This law represents the conservation of energy, which means or which implies that the potential difference is independent of the path. And here is discussed the connection of resistors. Similarly, as in case of the capacitors, we can connect resistors both in series or parallel. And as I already mentioned here, the rules are just the opposite. In case of series connection, we have to add the resistances in order to get the net resistance. And in case of parallel connection, we have to add the reciprocals of the individual resistances in order to get the reciprocal of the net resistance. And if we would like to get the electrical power, this electrical power is a dissipated power, which is defined as the energy converted per unit time. It's the product from the voltage and the current. And there are 2 alternatives how we can express this power by means of the resistance. It's either the resistance times the current squared, or the square of the voltage divided by the resistance. Now let's continue with the second part of the lecture. This is the magnetism. And first of all, we are going to talk about permanent magnets. Permanent magnets are objects that can exert magnetic fields on other magnetic materials. And here you are going to see that we have a very similar field concept that in case of the electrostatic field. However, there is a very big difference. Namely, meanwhile, in case of electrostatics, we might have separate isolated charges. In case of magnetism, the two poles, which are the analogies of charges for magnetism, we cannot separate. So there are no monopoles. These two poles are called South Pole and North Pole, according to the fact that the magnets are oriented along with the magnetic field of the Earth, and that pole that points toward the North Pole of the Earth, that's the North Pole of the magnet, and that one that is oriented towards the South Pole, that is the South Pole of the magnet. However, also here applies that the same poles repel each other, just like the same charges, applied charges, and the unlike poles, like South and North Pole, attract each other. Magnetic materials interact with the magnetic field, and according to this interaction, we can differentiate diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Diamagnetic materials are repelled by magnets. So as you see, the diamagnetic materials try to remove the magnetic field lines from their surroundings. Paramagnetic materials are attracted by the magnets, so that's the reason why the magnetic fields are concentrated within these materials. And ferromagnetic materials are also similar like paramagnetic materials. However, here the attraction is generally much stronger than in case of the paramagnetic materials, and they have a memory effect, so-called hysteresis. So if you perform a periodic process, then it will not take place the same way, and they can be turned into magnets. So they, in case of ferromagnetic materials, you can make this magnetic state permanent. Here you see three examples for the arrangement of magnetic field lines around different magnetic objects. And here I have to say that magnetic field can be created not only by permanent magnets, but also by current carrying conductors, because moving charges also create a magnetic field around themselves. Left, you see the magnetic field of a bar magnet. As you see, magnetic field lines always start outside of the magnet from the North Pole, and they go towards the South Pole. In case of a current carrying conductor loop, the magnetic field is concentric, so that the center is in the line of the the current carrying loop. So it's a kind of do-not shaped magnetic field in 3 dimensions. And if we have a current carrying wire, then these concentrically arranged field lines create a cylindrically shaped magnetic field, so it will have a cylindrical symmetry. Here we also quantifies the magnetic field around current carrying conductors. I will only show you the result. The upper formula shows you the magnetic field around the wire, and the lower formula shows you the magnetic field around the coil. As you see, the larger the current within a wire, the larger the magnetic field, and the further we go from the wire, the less the magnetic field. And beside the factor 2 pi, we have another constant here, this mu zero. The mu zero plays a similar role in magnetism as the permittivity in the electricity. This constant, this material constant mu, is called permeability. So also the name is similar as permittivity. And mu zero refers to vacuum. And if we put the current carrying objects into another surrounding, then we have to use the permeability of the given material. If we form from several loops a coil, then we get a homogeneous magnetic field inside the coil. Similarly, the magnetic field is inside of a bar magnet. And here the magnetic field inside the coil is directly proportional to the current in the coil. And it's the larger is the number of turns per unit length, which means that if you increase the number of turns, then you can increase the magnetic field strength. And similarly, you can increase this so that you compress the coil. So the same number of turns is in a less distance. What happens if we put an electrically charged object in magnetic field? Then the so-called Lorentz force or magnetic force will act on it. This magnetic force is directly proportional to the charge, to the velocity of the object, and to the magnetic field. This magnetic field is measured in Tesla. Tesla is the unit, the SI unit of magnetic field. In order to determine the direction of the magnetic field, then you have to use a vectorial product between the velocity vector of the charged particle and the direction of the magnetic field. And this is supported by the so-called left-hand rule. Here, in case of the left-hand rule, you have to use obviously the left hand. And the middle finger shows the direction of the velocity of the particles, so the direction of the current. Your pointer finger shows the direction of the magnetic field, and your thumb will point into the direction of the magnetic or Lorentz force. If we have a homogeneous magnetic field and we start a charged particle in this magnetic field, and this charged particle will move along a helical path. And this helical path is represented here in this figure. And the special case is if the initial speed is perpendicular to the direction of the magnetic field. In this case, they will move along a circular pathway. What's more, the angular frequency of this movement is also characteristic. This is called Larmor frequency. And this angular frequency is directly proportional to the charge of the charged object to the magnetic field, and it's inversely proportional to the mass of the particle. What's more, we can also calculate the radius of this pathway from the velocity. So meanwhile, the frequency is independent of the velocity. The radius will depend on it. These formulae play an important role in the particle accelerators, where charged particles are accelerated in magnetic field. They are called cyclotrons or synchrocyclotrons. And in the following, we are going to talk about an important law. This is the Faraday's law of induction. Faraday's law of induction is based on a dream. The dream was that Faraday wanted to separate the source of electricity from the place where it's consumed. And that's why he produced two connected loops, coils, and he thought that if there is a current in one loop, then this current can be transformed into the other loop. And he used a direct current, so a constant current, and he switched on the current in the first loop, and he measured the current in the second loop, and nothing happened. So the initial dream cannot be fulfilled. However, he observed a very strange phenomenon, namely, in the moment of switching on and off the current in the first loop, there is a current peak in the second loop. First of all, let's talk about the fact why it might be important to separate the source of electricity from the place of consumption. Do we have such an application in our everyday life? Yes, we have. If you have an electric toothbrush and it's battery driven, then if you just look at the two pieces that should be connected for charging the toothbrush, then you see no metallic connection. And it's good because in the bathroom there is a lot of humidity and it can be eroded or even a shortcut can be created. So it's a good idea. But let's go back to the initial idea. So with steady current, it does not work. However, the change in current, because switching on and switching off the current in the first loop involves a change in current. So this change in current might build up some movement of charges in the second loop. So that was the observation that led to Faraday to the fact that not simply the magnetic force, the magnetic field caused by the current causes the voltage in the second loop, but the change of the magnetic flux. Here you see the magnetic flux defined in the upper part of the slide. It's a kind of product, or better to say the integral, from the area and magnetic field. It can also be defined so that it's a scalar product from the magnetic field vector and the area vector. Okay, you might ask that, what does it mean, area vector? Area is not a vector. Area vector is defined so that the magnitude of the area vector is the magnitude of the area, and the direction is the direction perpendicular to the area. So now we have here a physical quantity that codes not only the size of the area, but also its orientation by means of a vector. And if we take the scalar product of this area vector and magnetic field vector, then we get the magnetic flux. And if this magnetic flux changes, either due to the change of the magnetic field, we can change the magnetic field, for example, by changing the current in a loop, or due to the change of the size or orientation of the surface area, then this magnetic flux changes. And this change in the magnetic flux creates a voltage. This is called induced voltage. Here in the Faraday's law of induction, we have an additional minus sign. This minus sign corresponds to the Lenz's rule. The Lenz's rule states that the current induced or caused by the induced voltage is always directed in such a way that its magnetic field counteracts the cause of the induction. Why is it important? Because if it were not so, then the induced voltage or the induced magnetic field could enhance the original magnetic field, and thereby an infinite magnetic field could be created. Obviously, it's not possible. From a finite magnetic field, we can't have an infinite magnetic field. So that's why we need this Lenz's rule in order to fulfill the conservation of energy. And there are two ways how we can induce voltage. First of all, with constant magnetic field, if we change the size and the orientation of the area. If we, for example, rotate a loop, a current carrying loop in constant magnetic field, and here the voltage is explained by the Lorentz force acting on the charge carriers in the conductor. The other option is that we have an area with constant size and orientation, through which there is a changing magnetic field, and this changing magnetic field causes voltage impulses. So this is the second motional, so-called motional induction. If we think back to the first option, then it will explain how we can create alternating current. The simplest generators contain a conductor loop with many turns, and they are positioned in a homogeneous magnetic field, and that's how we get a sinusoidally changing induced voltage. This induced voltage is directly proportional to the magnetic field used in the generator. It's as large as many turns we have, so the number of turns act as a multiple. The induced voltage is the larger the area of this loop, and the quicker we turn it, so the angular frequency of the rotation version also plays here a role in this formula. And then we have here a sinusoidal term. This sinusoidal term will describe the sinusoidal change in the voltage. So as you see, here we have a maximum value. The maximum value can be calculated from the product of B and N and A and omega, and then it's modulated by the sinusoidal term. Here you see these statements in details, and also the individual phases are represented here. So here, this is one cycle in the alternating current. And then you can see here in the upper line, which positions of the loop are associated with this. And then we have to talk about the transformers. These transformers have a very similar construction than the experimental setup of Faraday. Here we have a common core, and this common core contains two loops with different numbers of turns, N1 and N2. And if we connect voltage to the first primary coil, then we get another voltage from the secondary coil, and the ratio of the voltages are the same as the ratio of the numbers of turns. So that's how we can transform up or down the voltage. That's how we can make larger voltages or smaller voltages for a given voltage. This is how also your phone charger adapters operate. So I was quite quick. We have introduced, we have discussed both electricity and magnetism, and I really thank you for your attention. I finished the live stream. However, I'm glad to answer your questions if you should have. Thank you very much.